Hello, everybody. We start recording. Welcome to today's lecture, but I'm having something. Okay. This is my share screen. Now I understand. We will begin by fixing. Yes. We'll begin by fixing what was not done in the earlier lectures. And because it's something that I should have taught you in the previous semester, I'm not going to write it with my pen. I'm just going to show you how it looks like in the lecture notes. But this means I have to open them first, which is not so easy. Okay. There should be graph book, yes. Yes. Okay. So, Jacek, it's all your fault. You are absolutely right before. In order to make all these arguments precise, I should define vertex length of a path, okay? And of course, I should have done it in the previous semester, but I didn't because I didn't see it coming. So let me do it right now. Okay, for starters, because we will also, yeah, so here you see, I have this vertex length definition, but because we will apply it to all paths, let me remind you what we mean by an infinite path and what we mean by the end and the beginning of the infinite path. Okay, so let me highlight it. Okay. All right, so we decided to have infinite paths going left or going right or going into both directions. All right, so they can be infinite in the triple ways. We define an infinite path as a sequence, but the sequence can be labeled either by natural numbers, and this is the usual sequence as you remember from school. You can label them by the integers, and then this is a sequence going to plus and minus infinity. And then you can also choose your indexing set to be minus natural numbers, so then you go from 0 to minus infinity. So when you have natural numbers, then you surely have a beginning of your path, but you have no clear concept of what is the end of such an infinite sequence, such an infinite path. When you have minus natural numbers, then you have the end of the path obviously given, but it's not clear what should be the beginning. And when you have integers, then you have neither, all right? But we somehow decided to still define the beginning and the end for such infinite paths in the sense of having a convergence in discrete topology. So basically, if vertices stabilize from a certain moment and don't change, then we call it the end of a path, all right? So here you have these precise definitions that the end of an infinite path, if you are looking at natural numbers of integers, then the end of a path is an index W. If you have this property that there exists an M, that for every N which is bigger than M, the end of this vertex is always the same. So in a way, you basically end your path with a loop, and then you twist around it infinitely many times. And then the beginning is and then when you take minus natural numbers, then you don't have to have such a condition, because as I told you, the end of a path which goes to minus infinity, which sort of walks backwards, is of course the end of its last edge, which is E0. And in a completely analogous way, we define the beginning of an infinite path. Again, we have to consider two cases, but this time this is minus natural numbers and integers which are bundled up together, and the separate cases for natural numbers, because now we are talking about the beginning, and when you escape to plus infinity, then the beginning is clearly given. Yeah, and here you have examples. You can have a path marching from infinity, marching to infinity, and marching from infinity to infinity. Okay, so that's clear now, I hope. And here is the missing definition of a vertex length. And it is precisely what you expect it to be. So if my path is a vertex, then I say that this vertex set VP is just a one element set consisting of this vertex P. And then the vertex length is 1, because I define the vertex length of a path as the number of elements in the set VP. which is defined as follows. This is the set of all beginnings and all ends of all edges that build the path. And if you have no edges, if your path is just a vertex, then VP is just the element set consisting of this vertex, as I just told you. So then this vertex length is 1. So now we can correctly phrase the assumption that we used to prove a number of results a week ago. Of course, it's complete nonsense to say that there are no loops longer than 1, as Jacek pointed correctly to us before. But you can, it makes perfect sense to say that there are no loops that are of vertex length longer than 1. Yeah. So then the only thing that happens is that you have an edge which is a loop, and you can wind around it as many times as you want. And that's perfectly all right. Our claims are valid under such an assumption. It was just badly phrased. So now it has been corrected. That's the definition, and I corrected it everywhere in the lecture notes. Okay. So this is one thing I wanted to do. And another thing which should have been done in the previous semester, but it wasn't, simply because it came to my mind yesterday, was that we can have another very natural algebraic structure built directly out of paths without using any auxiliary algebraic structure like the field. So we discussed already that we can have a semigroup out of a space of paths simply by joining the empty path. But I think it's kind of useless. I mean, at least I couldn't make any use of it. But I think that the following structure is very natural, and it reflects what's going on later on in the world of path algebras. In particular, we have 2 propositions that have analogs for path algebras, and I'm also going to prove them today, this time with a pen on the blackboard or whiteboard. But I want to go first through these proofs in the case of constructing semi-rings directly out of paths without any auxiliary structure. This is simply, I'm not having any more input data. The only thing I have is a graph. Please remember that when we have a path algebra, we have one additional structure, you have your field. And you can have, for the same graph, completely different path algebra if you change your field. Now there is just a graph and nothing but the graph. And simply from the graph, I can build the following semi-ring. So I take any graph E, and I define RE to be the set of all, not just finite, of all subsets of the set of all finite paths in E. Then if I equip this set with a set union as addition, and the concatenation of paths as multiplication, this structure renders my set RE a unital semi-ring. And here the neutral element for addition is obviously the empty set, and the neutral element for multiplication is obviously the set of all vertices. And mind you, here I'm taking all sets, so I don't care whether E0 is finite or not. But I can go in the spirit of path algebras, and I can restrict the structure to the set of all finite subsets of FPE. So I have this superscript F to distinguish this semi-ring, which need not be unital, from the semi-ring RE, which is always unital, of all finite subsets. And you can see that these structures restrict, except for the multiplicative unit, which restricts only when E0 is finite. And I have REF as a semi-ring, as a sub-semi-ring of RE. And then the only non-trivial thing that I prove in this proposition, because every single argument proving these claims is completely obvious, the only not completely obvious part is to prove that this restricted semi-ring, this RFE semi-ring, is unital if and only if the set of all vertices is finite. And in this case, the unit is E0 as it is in this larger ring, larger semi-ring. This is not the ring, it's a semi-ring because our additive structure gives us only a monoid, not an abelian group, an abelian monoid, not an abelian group. Okay, so for starters, let me write it with formulas, what I wrote here in the proposition with words. Delete, okay. And now we highlight this so that it's completely clear what we mean by addition and multiplication. So I take any subsets in FP. So these are sets of finite paths in E, but these sets can be infinite. I'm not telling you that A and B are finite sets. So A plus B is simply defined as their set union. Obviously, the union of subsets is a subset. But now the multiplication, that's the beautiful part. I say that to multiply two subsets means constructing the following third subset, which consists of elements P times Q, where P is an element of A, Q is an element of B, and moreover, I take only such pairs that T of P is equal S of Q. So I simply take only all these elements that I can obtain in the process of concatenation. If there is P in A and Q in B that do not match in the sense of T of P being different from S of Q, then I don't have such a path in my set, all right? So it might easily happen that multiplying two very non-empty, very infinite subsets will be the empty set. And just for brevity, I'll denote this multiplication by juxtaposition, okay? And I decided to give you this proposition and another one in the same spirit, because it's something which is very useful and very much reflected in path algebras. And it's, yes?
Excuse me, I have maybe a question or
Oh, go ahead, Adam.
If we don't assume this condition that the target of P is the same as the source of Q, still using the definition of concatenation, which admits empty set as a result, we get a correct formula. So
yeah, but you see, Adam, look, Adam, we are not adding the empty path. There is no empty path now.
Yes, but still the concatenation of two paths which cannot be concatenated in the usual sense still gives us the empty set. So in this
of course. Of course.
If we don't assume this condition, we still get the same result. It is consistent.
Yeah, of course. But it's, I find what you're saying a little bit awkward, because the multiplication of paths should be a path.
Yes.
I'm simply saying that if I cannot concatenate these two paths, P and Q, then P and Q is not an element of my set which defines the result of multiplication. But that's, I think, agrees with what you're saying.
Okay.
Yeah, yeah, thank you. You wanted to ask.
Because in one case we get an empty set, and in the other case we get a set which has an empty set as an element.
Yeah, but this is exactly what I said. That there's no. It depends on what Adam really has in mind. Yeah, if you would like to use instead of FPE the semi-ring gamma, which is defined just above, then I could just say this is the semi-ring multiplication. But then that's not the same. You're right, and I'm not doing it. I find this construction, which I heard in a lecture, okay, I think it's interesting enough to mention it, that you can so easily turn FPE into a semi-group, but I don't find it useful. It exists, it's consistent, fine. But I prefer this one because it really directly reflects what's happening for path algebras. You will see, because I'm going sort of to do the proofs twice. Once I will show you it in this semi-ring RE, another time I will show you in the path algebra KE, that arguments are very much the same, even though they're not logically equivalent. Because in the case of path algebras, I'm taking finite linear combinations of some basic functions, but and here I'm taking arbitrary subsets, not necessarily finite. Yet the arguments are basically identical in the spirit, but I formulate them slightly differently. Okay. Okay, I hope I answered your questions. Now let's go further. And as I warned you, most of the claims is completely obvious. So when I take my set RE with the addition defined as the set union and with the empty set as the neutral element, it's evidently an abelian monoid. Nobody protests it, I guess, right? Set union is obviously commutative. adding, having a union of the empty set doesn't change the element. So that's evidently an abelian monoid. Now, when I take my concatenation multiplication, then again, this is clearly a monoid, but no longer abelian, of course. Right? Because yeah, of course, there's one more thing which should be verified, but is obvious here by definition is associativity. Of course, safe theoretical union is associative, and of course, concatenating of paths is associative. So that's you can of course go ahead and check it very carefully, but I think this is simply trivial. Simply because if you have a PQR, then you can shift parentheses PQ and then R, or P and then QR. That's just the same path. And maybe I should have been a bit more pedantic here to show the associativity. Maybe I will add it later on in the lecture notes, but I think that this is completely clear. Any objections that this is a monoid? With E0 being the neutral element? Well, maybe this requires a little bit of, okay, so why don't I go and share whiteboard? Sorry, this is the wrong, and maybe this one. Now I have to stop share and start sharing again. What? Okay. 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 Right. So with associativity, so let's say we have what? A, B, and C. Okay, so if I do it this way, I will have, okay, let me write it like this, all paths PQ, such that P is in AB, Q is in C, and T of P equals S of Q. Okay, but what does it mean that P is in AB? So now I can write it down. I write P as, I don't know, RS. So these are all such RSQs that R is in A, S is in B, T of R is equal to, I'm sorry, S of S is a bit ridiculous, but I hope you can forgive me. And then, of course, we don't lose this condition that Q is in C. And what is the end of P? The end of P is the end of S. And the end of S is equal S of the beginning of Q. So we arrived at RSQ. And well, if I am pedantic, I should write it like this, with parentheses around RS. And if you look here, so I have R in A, S in B, Q in C. And I say that the end of R is the beginning of S, and then the end of S is the beginning of Q. And I can easily imagine that if I do it the other way around with parentheses shifted, I will arrive with precisely the same definition, except I'll have R and SQ. So the associativity and here the same stuff, okay? So the associativity of a concatenation gives me associativity of a multiplication here. Okay, and now with a neutral element. So in general, you should note that if you have a set A, which is a subset of E0, so we take only paths of length 0, and vertex length 1, And when you take any other element B, so if you want, well, maybe I should be consistent. Let me write it as a subset of FPE. And basically A times B is a subset of B. So these are all P in B with a property where S of P is in A, right? This is just choosing a subset. So when your A is equal to E0, this condition is vacuous. And so obviously you get that E0, oh, sorry, times B is B. And likewise, when you have B times A, then these are all P in B with a property that now T of P is in A. So again, when A is E0, this is a vacuous condition, and I have that B E0 is equal to B, okay? So I considered it as completely obvious and didn't type it up. But maybe it was worthwhile to write it down. Okay, now I have to go back. So again, I stop sharing. And I start sharing my screen. Share. Voila. And here we are. But now, okay, so we have two monoids, one abelian and one not. Both are unit, yeah, well, actually by monoids, so that have neutral element. And now I claim that that the bilinearity of a multiplication map is also obvious. And let me not write it down. This is exactly in the same spirit in which you have it, A union B parenthesis intersected with C is A intersected with C union B intersected with C. That's exactly the same phenomenon. You see it in exactly the same way. There's nothing more to it. And you can see it whether you have this intersection on the left or on the right. Of course, it's more complicated because you have these concatenations. These are not just intersections, but it works in precisely the same way. You can prove that this is sort of if you're on the distributivity of addition with respect to multiplication. And since they are both defined in terms of sets, you can very easily prove that one set is a subset of the other, and the other one is a subset of the first one. So that's really obvious. And thus we get a unital semiring, right? Because what is a unital semiring? Well, you have to have such two monoids, one is abelian, one whatever, and then they have to be compatible in that sense that the multiplication map, so the monoid structure, the multiplicative, non necessarily abelian monoid structure, has to be distributed bilinear with respect to the monoid structure, which is abelian. Okay, and then we have a unital semiring. So I told you, first part is completely trivial. So now we go to this restricted semiring. And well, for starters, it is obvious that both the addition and multiplication restrict to RFE, and the empty set is no doubt finite. So the neutral element of the abelian structure is contained in the restricted part. What is not in general contained in the restricted part is E0, because if E0 is infinite, then it's an infinite subset, not a finite subset. And here RF is defined as taking only finite subsets of FPE. Okay, so addition restricts, multiplication restricts, and the neutral element for addition is in the restricted subset. So this way, we obviously have that RFE is a sub-semi-ring of RE, not the unital one, but sub-semi-ring. And don't even think that if it's not unital, that is an ideal. No, it's not an ideal. This is not an ideal in the big ring. But now if E0 is finite, then it is an element of RFE and serves as a multiplicative unit. That part is clear. If it is a multiplicative unit, which I explained to you just a second ago, in the big semi-ring, of course, it is also a multiplicative unit in the smaller one. It's just a question whether or not it belongs into this restricted semi-ring. So that part is clear. And now there's the only non-trivial argument in the whole proposition, which I think is cute, and you argue in precisely the same way with path algebras, as you will see in a short while. Now we want to prove that E0 is finite when the restricted semi-ring is unital. That's the implication, which is not so completely trivial. So to this end, we assume that RFE is unital and 1E is its unit. And then we define the following set X. This is the set of all beginnings of all paths which belong to 1E. So remember, 1E is simply a finite subset of the set FPE. Okay, because 1E is an element in RFE, and RFE is the set of all finite subsets of FPE. So this is a finite subset of FPE. So I'm taking all paths which belong to these finite subsets. Well, this can be empty, we don't know. For the time being, it can be empty. Then X is also empty, no problem. I don't care, it's also fine. Everything works with argument if E is the empty graph, no problem. So now, if E0 were infinite, so that's our assumption that 1E is unital, right? I'm just using assumption that RFE is unital. But now, if RFE is unital but E is infinite, we immediately get a contradiction. So suppose E0 is infinite, but then because it's infinite and X is finite, then there must exist a vertex V which is not in X, right? But then we get immediately the desired contradiction, because when I take the one element set is a finite set, times 1E, then I see that it must be the empty set. Well, because, oops, I don't know what happened. Because V is not a beginning of any path in 1E. So whatever concatenation with this vertex of any path in 1E you try to do, but we will not concatenate. So the set will be empty. But the empty set is not the same as the set containing one element, which is V, which it should happen if 1E is the unit. So we have this contradiction here. So this is why I have if and only if, because what we just proved is not only that finiteness of V0 implies that RFE is unital, but also the unitality of RFE implies the finiteness of V0. Okay, and the argument for the unitality of the path algebra will go exactly the same way, but it'll be slightly differently denoted. And mind you, well, okay, no, here it's actually very similar because we take very restricted subsets. Okay. So that's the end of the proof of the first proposition. And what I like about it is that it is pure. I mean, you only have paths, you only have a graph, nothing more. There is no any additional structure whatsoever. Yet it reflects everything, maybe not everything, it reflects what happens later on with path algebras. Now, another proposition, which I find important, because you want to understand when your path algebra is commutative. And the argument for the commutativity of a path algebra is basically identical as the argument for the commutativity of RE, and the condition is exactly the same. And here I decided to take RE, this full unital semi-ring, well, because it's bigger. And if this is commutative, then its subring is commutative. So somehow, well, that's an additional question to see if the same if and only if holds when you get the restriction. But I don't want to exaggerate. We are not writing an encyclopedia. I don't want to, this is not Bourbaki. I don't want to check absolutely all possibilities, only sort of the most interesting ones. Okay, so the claim is that the semi-ring RE is commutative if and only if the set of edges is empty, or alternatively, each edge is a loop starting and ending at a different vertex. So in other words, the only thing that you have is as you can have as many vertices as you want. And then the only edges are loops. And the given vertex, you have only one loop. Sorry, one length, one loop. Yeah, because of course I can then wind around as many times as I want. But when I look just at E1, at the edges, I have just a bunch of loops. My edges are loops, and each and every of these loops starts and ends at a different vertex. Okay, and here the reasoning is not so completely trivial, so I hope it will be more enjoyable. Of course, nothing here is difficult, but at least it's not so completely trivial as with the previous proposition. So for starters, let me assume that E1 is the empty set. Then obviously all elements of Re are subsets of E0 because the only paths are vertices. But if my paths are vertices, then the multiplication is simply nothing but the intersection, right? And you can use the formula which I wrote for you before. If I have a subset of a set of vertices times any other subset, then what I obtain is a subset of the subset on the right, which has the property that each of its paths begins at my subset A. And then if I multiply from the other side, I have the same, but with the ends. So basically, when you look at this formula, because here all paths are vertices, you simply have, so these are all vertices in B that are also vertices in A. Well, but this means the intersection. Okay. And I hope you agree that the intersection of sets is commutative. And this is the same as BA. So R is commutative if you have no edges. But now let me make it slightly more difficult. And now let me assume that E1 consists only of loops starting at different vertices. Then what are my paths? These are either vertices or loops of vertex length 1 starting at different vertices. Okay. That's all I've got. These are my all paths. There are infinitely many of them, obviously, but that's all I've got. They have a very particular structure. So now let's take C and D. Let's take C and D to be subsets consisting only of loops of vertex length 1 starting at different vertices. So I'm somehow, this is of course the disjoint union. And now I'm looking at subsets in this part of my FP, okay? Then, and remember that what is a loop of a vertex length 1? This is simply an edge to some power, okay? So I take, so when I multiply C and D, by the very definition, I get EM times EN, where EM is in C and EN is in D. Right, because there's the only way I can concatenate. Since all elements are just loops, starting and ending at one and the same point. When I try to concatenate, the only way I can concatenate is that I take loops that start and end at exactly the same place, which means I'm taking the same edge to some possibly different power. Yeah. So I have EM times EN, where EM is in C and EN is in D, but obviously adding natural numbers is abelian. So EMN is the same as ENM. Okay, so that's the same as DC. So multiplying elements that come from here, subsets of this set, is also abelian, is also commutative. So there's one more thing we have to check, sort of the cross term. How about multiplying a subset of E0 with a subset of this second part? Well, it's actually even easier. I take A to be the set of vertices, A set of vertices, so A subset of E0, and D a set consisting only of loops of vertex length 1 starting at different vertices. Okay, And what is AD? According to this formula that I gave you on the whiteboard, these are all elements in D with a property that they begin in A. But because these elements are loops, when it's the same as saying that these are all elements in D that end in A. But that's exactly the result of multiplication of D by A on the right. So AD is equal to DA. Again, we get commutativity. So finally, we just have to observe that any element of RE can be written as a sum of A and C, where A is a subset of E0 and C is a subset of the second part. Okay, in fact, this decomposition is unique because this is a disjoint union. These two sets don't intersect. So then I have A plus C times B plus D, where B is the same type as A and D is the same type as C. So I get 4 terms. One term is just commuting subsets of E0. Another term is commuting subsets of this loop part. And then I have 2 cross terms, but everything commutes. Okay. So if I have x plus y times x prime plus y prime, and x commutes with x prime and commutes with y prime, and y commutes with x prime and y commutes with y prime, then the addition commutes. Okay, so this proves that R is commutative. And now we have an exercise in logic. So Jacek, please watch out, because you like correcting me in such things. I hope I didn't screw it up this time. But we have to unravel what it means to prove the other implications. If this condition is logically a little bit subtle, so it takes a while to unravel what it is that we want to prove. What does it mean to prove the opposite implication? So to prove the opposite implication, we have to negate the statement that E1 is empty, or each edge is a loop starting at a different vertex. That's exactly what we said in the proposition, but now written in symbols. So either E1 is empty, and if it's not empty, then it consists of edges that are loops starting and ending at different places. Okay. So how do I negate it? Well, the negation of an alternative is a conjunction of negations. So here I should add E1 is non-empty, but simply when I write E1 is non-empty and the rest, then somehow that's included. Because if I say E1 is non-empty and if there exists an E in E1, well, then obviously existence of E in E1 implies that E1 is non-empty. And here I have an existence of even 2 elements in E1. So this conjunction with E1 is non-empty is vacuous. I can skip it. So this is why I look on at this alternative, right? So now I'm looking at the negation of this one, but here's the negation of a conjunction. So it will be the alternative of negations. So either what I've got is an edge which is not a loop, or I have 2 different edges that simply don't begin at the same point. Okay. So let's see. Where's delete? So let's see how it happens. So first assume that there is an edge which is not a loop. Well, if I have an edge E which is not a loop, then I do the following calculation. I take the subset consisting of the beginning of E, that's a vertex, it's fine. And I multiply it by the set consisting of just one element, which is the edge itself. And obviously these 2 sets multiply to the set E, which is definitely non-empty. So it's not the same as E times SE, because remember, E is not a loop, so its end is not its beginning. So multiplying by SE from the right will give me the empty set. I cannot concatenate E and SE with SE being on the right. So RE is non-commutative. Okay. And now here's a certain minor logical subtlety. Well, now I should take simply that part, that I simply have 2 different edges that have the same beginning. Well, but if they are not loops, then I'm already done. So I can, without the loss of generality, assume that the other condition, sort of the part of this condition which is not already in the previous condition in my alternative, it's simply that there exists two loops that are different but have the same beginning and the end. Okay. Of course, if I read this condition, it doesn't mean that they are loops. It means that they are edges that are different but begin at the same place. But if one of them is a loop, I'm already done. I already know that the semi-ring is non-commutative. So that's why about the loss of generality, what I'm doing is the following. I take two different edges E and F such that they are loops and they begin at the same vertex. But then if I multiply the set consisting of just one element E with a set consisting of just one element F, of course I can concatenate them because they are loops that begin and end at the same vertex. So I have a path EF, but this is not the same as a path FE, because EF and FE are different paths because E and F are different edges. Okay, so EF and FE are different paths. Going first the yellow loop and then the green loop is different than going first the green loop and then the yellow loop. Like in a free group on two generators. You have two different letters. AB is not BA when you have a free group. Okay, but now FE is obviously the set F times the set E. So that's non-commutative again, and we are done. This proves the other implication. And lo and behold, because this argument, so the other part is similar, but I could write it differently. But that part is just so completely identical in the case of path algebras that it simply didn't make sense to rewrite it for path algebras. That argument goes verbatim for path algebras to prove that if my graph is not of a form which I prescribed, then the path algebra is non-commutative. This is an identical argument, verbatim, except writing curly braces signifying subsets, I write chi. So I would have here chi SE times chi E, and instead of the empty set, I would have 0. So I decided not to rewrite it in the case of path algebras. Okay, so I think this ends the reminder from the previous semester. I mean, I wrote it yesterday because it occurred to me yesterday, but it should have been taught in the previous semester. I suppose now I can go back to the blackboard. Yes, I can now go back, sorry, the whiteboard, and reprove these things, but now in the setting of path algebras. Okay, so I stop sharing and I start sharing. Okay, let me dig out my notes, freshly printed. Okay, so now our proposition is that E be a graph and K be a field. In fact, here you see, Maybe that's the beauty of my slight detour into the strange world of semi-rings. But you see that the field here is irrelevant. If I had this algebra over a commutative ring, it would be fine. Nothing changes. K doesn't play a role in this argument. Okay, you have to be careful because sometimes it's important. You have some claims, like when we're looking at ideals in matrix algebras, then it's important that if something is non-zero, then I can invert it and normalize things. But here it's completely irrelevant. I don't have to invert any of my coefficients. I don't have to say that I have a basis, I have a vector space. No. And now we understand the source of it, because the source of it is our two propositions proven in the world of pure semi-rings. Okay, but let me finish writing this proposition. Then the path algebra KE is unital if and only if E0 is finite, in which case the unit of a path algebra is the sum over all vertices in E0 of chi labeled by these vertices. Okay. Proof. So I warned you that's exactly the same argument as before. Not exactly. This is why I want to do it. It's you can read it out that this is the same logic, but I think there is no harm to rewrite it so that you see the similarities, which are of course very strong. So if I take, well, first I can say that the proposition is trivially true if E is empty. So let me not consider the empty set. Let me not say that I sum over the empty set. The proposition is just trivial when the graph is empty. Okay, and when graph is non-empty, then E0 is non-empty, so that sum is really a sum over a non-empty set. Okay, for any P in FPE, we obviously have that if I take chi P and multiply it by the sum over all these of chi V, well, then this will be the sum, but now with chi P chi V. And obviously the only element of the sum survives when V is equal to TP. And then it will be just chi P chi TP, which is chi P. And exactly the same argument goes when I put chi P on the right. So first I can put it inside the sum, and then I note that the only element of the sum that survives is when P is now equal to the end. Sorry, when P is equal to the beginning, well, sorry, when V is equal to the beginning of P. So it will be chi S P chi P, but just as before, but just chi P. So nobody can question whether this is a unit. This is the unit of my multiplicative structure. And yeah, well, I mean, this argument, which was, remember, the only non-trivial part for a restricted semi-ring, is very much similar. So assume that KE is unital. Okay, then it must be, I must be able to write it in terms of some basis elements. So there exists a unit, and I can write it down as the sum, finite sum, say from I equal 1 to n, lambda I chi pi, right? Because all these chi p's form a linear basis for KE by construction. Okay. But now, since 1 KE times chi v is equal chi v, which is not 0, and this is true for all vertices, okay? That's true for all vertices, that 1 times chi v is equal to chi v, and chi v is different from 0. This is true for absolutely all vertices. Then we infer that E0 must be a subset of the set of all endpoints. Sorry, Pi. And you run your I from 1 to n. Right, because the only way you can have that chi v times such a sum is equal to chi v when you have there must exist a path pi which ends at v. If all paths pi do not end at v, then this multiplication would yield 0. And chi v is not 0. So it means that there must exist always, for every v, there must exist a path pi, and there are just finitely many of them, n, such that the end of pi is equal to v. So this means that because it's true for all vertices, it means that the set E0 is contained in the finite set of all endpoints of pi's. There are at most n many of them, okay? So E0 is finite. It's basically the same argument as before, just written differently. So I thought there would be no harm repeating it. And this ends the proof of this proposition. I presume there are no questions. So now we do the other analogous proposition. Again, we have precisely the same preamble. Let E be a graph and K be a field. Let me keep writing this. The path algebra KE is commutative if and only if E1 is empty, or each edge is a loop starting, ending, which is the same thing, at a different vertex. And you know very well by now what I mean by this. So that's exactly the same type of a proposition. It's just now that instead of saying that our semi-ring RE is commutative, we say that the path algebra KE is commutative. And the first part of the proof is worth repeating. because you can write it in a slightly different way. And now remember, these are different things, because here we are talking path algebra, so finite linear combinations. So when we have an element in our path algebra KE, then we are talking only about finite subsets of FPE, okay? Because basis elements are labeled by paths in FPE, and because we use only finite linear combinations, well, our sums are in fact over finite subsets of FPE. So we are in the realm of this restricted ring. But our proposition was proven for the full ring, this is full semi-ring, not the restricted one. So there are some slight differences here, okay? So for starters, assume that E1 is empty. So you have only vertices. Rather than for all vertices VW that are different, you have that chi V, chi W is 0 and is equal to chi W, chi V. So KE is commutative. Right, because of course chi V commutes with itself for any V. So you only have to look at cross terms, and the cross terms are the form chi V, chi W, where they are different. And anyway, that's remember we already established that the path algebra, in the case you have no vertices, this is just function algebra with pointless multiplication. So it's obviously commutative. So that's not a big deal. Okay. Now let E1 consist only of loops starting, ending at different vertices. By the way, Jacek, I have the feeling that I'm getting used to writing on this. So you have been right, I think. Yeah, it's a very slow process, but today for the first time, I feel that it's easier for me to do it than it was at the beginning of the semester. Okay, and look at our arguments now. So then, of course, it's basically the same argument, but it's phrased slightly differently. For any paths PQ, with, say, different endpoints, which also means different starting points. Have chi P, chi Q is equal to 0 is equal to chi Q, chi P. Okay? Right, because if they end at different places, they then also remember TQ is equal to SQ. So you cannot concatenate, so chi P, chi Q is equal to 0. And by the same token, chi Q, chi P is equal to 0, because now you can say that T of P is equal to S of P. So the end of Q is not the beginning of P, so you cannot concatenate in the other way around. Okay, so that's 0, whichever way you multiply. Now, if it so happens that T of P is equal to T of Q, then remember, this is what is very important, that the only paths starting at a given vertex are either a vertex itself or a vertex length 1 loop. Yeah, because we might have an edge which started with vertex and which ends at the same vertex, and then you can wind around as many times as you want. So when I have P and Q that start and begin at the same vertex, it means that I'm taking exactly the same edge, which is a loop, but I can potentially take it to a different power. So this is what I explained to you before. So I let me not write it right now. Then we also have commutativity, because when chi P chi Q equals to chi PQ, but because P is e to some power and Q is e to some other power, that's the same as chi QP, which of course is chi Q, chi P. So hence again, Ke is commutative. And to prove the opposite implication, we reason precisely something is wrong. Precisely as in the semi-ring case. Here really doesn't make sense to rewrite it because the argument is verbatim identical. As I told you before, I just swap curly braces indicating that I'm taking some subsets into these basic functions chi. So instead of having the set SE times the set E, I have chi SE times chi E. Right, so that really doesn't make sense to repeat it. I don't have any other way of arguing here. Well, you can also say that here that's basically the same argument, but somehow, I don't know, maybe it's better to write really a complete full proof for the semi-ring and then just say here that this is analogous. Doesn't matter. What is important that you guys understand this reasoning. It's not so completely trivial, and you see that it works just as well in the semi-ring world of pure paths as in the case of path algebras. And I emphasize that these things are not so completely logically equivalent because over there we're taking arbitrary subsets, including infinite subsets. And this somehow indicates that we could just as well take fine infinite linear combinations of chi-Ps. It would make sense. Instead of having finitely supported functions on FP, we could take all functions on FP, and we could make sense out of it. So the upshot of somehow realizing that there is a semi-ring structure behind, a very clear semi-ring structure behind our path algebras, points at some alternative definitions of path algebras, or having algebras which are path algebras in a different sense, if you will. Any questions thus far? Because I think we leave this world of elementary facts concerning path algebras. And now we enter Anya's territory. So I apologize. I asked Anya to prove an incorrect theorem. And luckily for her, she didn't do it. But now I want to explain what I screwed up, and I'll write it about it, and then Anya will carry on in the recitation class. But this part belongs to the lecture. I want to make it part of the lecture notes. So now we are moving into the radical territory, and I promise you this is the last statement about radicality. You see, remember, yeah, I think I've got it. Remember, before we had this corollary, that told us that if I take KE and kill the radical, then this will be, and I think I had the notation EJ, then this will be the path algebra of another graph EJ, where the graph EJ is now composed of all paths which are not in the Jacobson subset. Okay, well, we defined it before. I don't want to do it again. So basically, what I do, I remove the Jacobson edges. Okay, I have EJ 0 equal to E0, so I keep the vertices alone. I don't change them. But now I say that EJ1, this is simply E1 less Jacobson subset. So I remove Jacobson edges from the set of all edges. Okay, and this is obviously a subgraph, and it has this property that this is naturally isomorphic with this quotient algebra. So this is telling you the story of how to kill the radical. How can I express my path algebra? How can I express my structure, which I obtain after killing the radical, in terms of graphs? That's the answer. But now I want to go the other way around. I want to ask a symmetric question. Now I want to say what happens when I remove the part which is not in the Jacobson radical. Yeah, so here I'm killing the Jacobson radical. And now I want to do something opposite. I want to remove or kill, if you want, I don't know how to phrase it, everything which is beyond Jacobson radical. And more precisely, I want to have this Jacobson radical as huge as it can be, which means the arrow ideal. Of course, I cannot go beyond the arrow ideal. I cannot enter this commutative territory of commutative functions of algebra, functions on vertices, finitely supported functions on vertices. However, here we're in the radical territory, so these are unit of path algebras, so E0 is finite. So forget finitely supported; it's automatic. Okay, and in order to unravel it, that's not as beautiful as in this case, but I think it's sufficiently nice to say it. I have no idea what it might be good for, but it's something that had occurred to me more or less 10 years ago when I was teaching this stuff in Canada. And I don't know how much it is worth. I simply completely forgot it after so many years, and that's why I asked Anya to prove a wrong thing. But let's now do it correctly. And in order to do it correctly, first I must give you a definition, which I haven't encountered anywhere, and which I find extremely natural. And only with the help of this definition, we can correctly phrase the problem and solve it. I mean, I'll phrase it, Anya will solve it. Okay, so let E be a graph and JE be the Jacobson subset of FPE. We say that a path in the Jacobson subset is J indecomposable so that's our definition. This is what we define. Whenever you have the following implication. If P is equal RS, but it implies that either R or S is not in the Jacobson subset. Okay? So that's the definition. If I can decompose my path into the concatenation of two subpaths, then at least one of these subpaths must be beyond the Jacobson set. And here I owe you two comments. the first comment is that you cannot have, this must be an alternative, it cannot be a conjunction. Because if you would have it both R and S are beyond the Jacobson subset, then their multiplication would be beyond the Jacobson subset and we'd get a contradiction. But remember, the complement of a Jacobson subset is a multiplicative set. And by the way, this is also why I'm so happy I came up with this semi-ring structure, because in fact we are using it. When we are doing our algebraic calculations, remember the proofs and so on, it's all the time what we are doing. We are in fact using this concatenation multiplication of elements of my semi-ring. So that's useful. That's useful. In fact, I was hesitating for a while about proving these matrix theorems of a semi-rings because they work just as well. I can again say that at least as restricted semi-ring of a graph can be written down as an appropriate matrix semi-ring. There's no problem. You can do it by exactly the same argument. And then you can go to the upper triangular case for some appropriate almost acyclic graphs, finite almost acyclic graphs. But I decided that it's not interesting because the motivation for path algebras is clear. When we write this isomorphism of the path algebra with matricial form, then in concrete examples, we can immediately nail down what these path algebras are. These are hypertriangular matrices, or these hypertriangular matrices with 0 here and 0 there. Or it's something slightly more complicated that you put polynomials here and there's a field there. But then these are very concrete algebras that you unravel. But when you try to do the same for the semi-ring, you don't get anything interesting. In fact, you see, the upshot of path algebras is that you recover so many important algebras, polynomials, tensor algebras, and much, much more. These are just special cases of path algebras. And many matrix type algebras. But when you look at this semi-ring, which we just defined, you don't get anything interesting, really. You get some weird semi-rings. So for instance, as you could see, right, as you could see in the proof of one of his propositions, remember the assumption that E1 is empty, then all paths are just vertices. And then the multiplication, this concatenation multiplication is nothing but set intersection. So that's exactly the set theoretical semi-ring. If I have any set, and I take the set of all subsets, so the set of all subsets is in an obvious way a unital commutative semi-ring, with multiplication being intersection and addition being union, right? This is for any set. It's completely general. So that's the natural part. And if you would say, all right, let my graph consist of just one edge and one vertex, so it must be a loop. So in the case of path algebra, it's beautiful because you get polynomials in one variable. But when you would look at the semi-ring, you get something weird. You look at all subsets of natural numbers that you add, and the addition is that you take all natural numbers that you obtain by adding natural numbers which are such that one is with one subset and another one is another subset. It's nothing particularly exciting or natural. So that's why I decided that even formulating these propositions of matricial structure of a semi-rings is true, but boring. I mean, it's irrelevant. I don't see what it serves. But these two propositions I find important because you want to, which we proved for the semi-ring, because you want to know when it is unital, you want to know when it is commutative. These are fundamental questions about the structure that you have. And it's beautiful that the answer is exactly the same for the semi-rings as for the path algebras. And I think it gives you a deeper understanding of why the proofs work for path algebras. Okay, this was just a detour. Let me get back to what we are here. So you see, this is important that this is really an alternative. If I would write here conjunction, that would be impossible. This would be nonsense. You cannot have it, because the complement of J, the Jacobson subset, is multiplicative. And also note that this concept doesn't make much sense if P is not in the Jacobson subset. Because you could think, all right, why do I say what is a J decomposable path, which is an arbitrary path, perhaps beyond the Jacobson subset? Okay, so let's take a path beyond the Jacobson subset. If you can write a path beyond Jacobson subset as RS, then of course it's a must. None of them can be in the Jacobson subset. It's trivial. It's immediate, because if any of them were in Jacobson subset, remember that this has ideal like property. It is an ideal property in the semi-ring, which we just defined. So that would be always given. Yeah? Then both must be beyond Jacobson subset if P is beyond Jacobson subset. Okay. So that's why it doesn't make sense to define J indecomposability for a path which is not in the Jacobson subset. But here, this is quite an important concept. And I hope that you can see that a path is J decomposable if and only if it contains only one Jacobson edge. Okay? Imagine that you have a path. Oops, I have to change into a pen. Imagine that you have a path which is in the Jacobson subset. So remember, we already discussed it. So I know that a path which is in Jacobson subset must contain an edge which is in the Jacobson subset. So here is my Jacobson edge, and here is the beginning of this path and the rest of the path, but in the middle, I have my Jacobson subset. My Jacobson edge, sorry. And obviously, such a path is J decomposable, because anyway, you split it into the concatenation of two subpaths, this edge E can be only in one of them. It cannot be in both of them. So then it means that one of these subpaths has the property that it contains absolutely no Jacobson edge. But it means that every edge is beyond the Jacobson subset. And by multiplicativity of this complement of a Jacobson subset, you have that this path is not in the Jacobson subset. So the condition of decomposability is satisfied. Okay. And very much you can argue that if you have two different Jacobson edges in your Jacobson path, then obviously you can split. Just take one subpath which contains E and another subpath which contains F, and you are done. So that's not J decomposable. So in other words, you can say that a path P in the Jacobson subset is J decomposable if and only if it contains precisely one Jacobson edge. Okay. So that's the meaning of its definition. And now we can phrase, finally, we can phrase the definition, I mean the proposition, which Anya will prove. Today. Okay, the proposition as follows. Since this is the radical area, so I assume that my path algebra is unital. Then there exists an acyclic graph let's call it EAC. So AC stands for acyclic, not for Alencon. EAC, such that, oops, there is a unital algebra homomorphism call it F from KEAC to KE. So remember, in this corollary where we were killing the Jacobson radical, we had a map from KE to KEJ. Now I'm going the other way around. In order to sort of kill, remove, disregard the part which is beyond the Jacobson radical, I have to move into the other direction. I'm constructing a graph which is sort of above E. Okay, not the subgraph as before. Okay, although I'm not saying that E is a subgraph of EAC. Of course, it's not. It's more subtle. It's more complicated. But the natural map. I mean, the only way you can write the map is from this new acyclic graph path algebra into the given path algebra, not the other way around. Okay, satisfying the desirable property that F of a Jacobson radical of KEAC is equal to the Jacobson radical of KE. Now, please remember that F is neither an injection nor a surjection. That's just a homomorphism of unital algebras. You'll see when Anya will construct it today. And in general, it's not true that if you have, I mean, in order to prove that if I have a unital algebra homomorphism from A to B, in order to prove that F of the Jacobson radical of A is contained in the Jacobson radical of B, so that, you know, the Jacobson radical is mapped into the Jacobson radical by my unital algebra homomorphism. I remember I did it, but I needed to assume that F is surjective. I don't have a counterexample of hand, but please correct me if I'm wrong, but I don't believe it works. I think you can cook up a counterexample that F of J radical of A is not inside J radical of B if F is not surjective. I mean, I don't have it offhand, but I believe it's doable. So that's something particular to this situation. It's not even inclusion is guaranteed. And here I claim more than the inclusion. I claim the equality. So if you want, I'm presenting the arbitrary Jacobson radical of an arbitrary unital. I present the Jacobson radical of absolutely arbitrary unital path algebra as the image of the Jacobson radical of an acyclic graph. And there in this acyclic graph, as we know from our beautiful theorem, this is the same as the arrow ideal. Right, so we somehow removed all the loops, we delooped our graph, we got an acyclic graph with this nice property that its Jacobson radical represents the Jacobson radical of KE, because that's just a surjection onto this Jacobson radical. So every element of my given Jacobson radical can be written down as the equivalence class of elements of this Jacobson radical of the acyclic graph. Okay, but, and this is what I initially intended for the exercise, the situation gets better if you throw in one extra assumption, which is quite strong, yet it is satisfied in the plethora of interesting examples, including, you know, generic Podley spheres from non-commutative topology and so on and so forth. So that's not an example without, sorry, that's not a condition without interesting examples. Yes, it cuts out maybe not majority, but a significant part of your examples, but you are left with still things that are interesting. So let me write it down. And moreover, oops, but I need a pen to write it. Moreover, if E is a graph satisfying the additional condition that all elements of its Jacobson subset JE are J decomposable, then in fact F is injective. So it gives an isomorphism of these two Jacobson radicals. So the Jacobson radical of EAC, sorry, of KEAC is isomorphic with the Jacobson radical of KE. And that's what we wanted to prove. But in the exercise, there was a missing assumption. I mean, you have to assume that the graph E has this strong property that each and every element of its Jacobson subset is J decomposable. And that's not an obvious assumption. But I forgot it. It was almost 10 years and I forgot it. And only when having a discussion about it at the Blackboard, I realized it. So Anya will prove it today in the recitation class. I have only 3 minutes left, so it doesn't make sense to start a new topic. So maybe I will give you a sneak preview. So spoiler alert, I will tell you what Anya is going to tell you. That how you get this EAC, because it might be also part of the proposition, right? I could have phrased the proposition in such a way that I construct EAC and then I define F and then I make my claim. But I decided not to do it because it's not so important of what precisely this EAC is. What is important when that it's an acyclic graph. Yeah. So I can find an acyclic graph and then the Jacobson radical is a acyclic graph, which means the arrow ideal in this the path algebra is exactly equal to my given arbitrary Jacobson radical. I have this presentation. So this answers the question of how we go the other way around. And well, so what we will have to do, we define EAC 0 to be just the same as E0. So vertices are untouched. But now we define EAC 1. And now I can actually guess what I'm going to write. I say that the edges are J in decomposable paths in JE. So I have incredibly many edges, right? Typically, I have infinitely many edges, which is all right. So every J decomposable path which I have in JE, I turn with a magic wand into an edge. Okay. And of course, you see that this is a subgraph because, that this is a graph because the ends and the beginnings of any paths in E are of course in vertices of E, and E0 AC is equal to E0. So you have well-defined source and target maps induced from the graph E. So this is really a graph, all right? And it's also obvious now how to define a homomorphism because you know what to do on generators, right? obviously I'll be identity on vertices. So chi v will go to chi v, where v is a vertex. But now when I take any edge in EAC, and take chi e, where e is my edge in EAC, then of course I'll map it to chi labeled by the path to which this edge is assigned. Okay. And then you can check that it's an algebra homomorphism, and you can check that it's injective when all paths in JE are intercomposable. And Anya will explain why it fails to be injective when this assumption is missing. Oh, but it's already 1 minute over time. So let's have 29-minute break, and I will see you in 29 minutes at the reservation class. I stop recording. Thank you.